All right. What up? All right, everybody. Tom McGurl back for final chapter, chapter 20, Learn Rust live series. Another episode. Don't worry, this isn't the final episode of the stream by any means. I mean, it might be the final one for the Rust book if we can get through it all tonight, which I'm willing to go late to do so. But it won't be the final episode of the stream, just the final episode of the book, probably. I'm excited. Why am I excited? We're on chapter 20. We started this. When did we start? We'll take a look. Let's take a look. When did we start this? We're going to go off our YouTube videos. So we started this back in 6 months ago. So we're looking at what? What's the date on this? No thanks. September. Duh. Can't do math. In September. We started this in September. We did chapter 1, 2, 3, 4. You know, you can count, right? We did them all. We did the rustlings exercises. And here we are on chapter 20 of the book. It's been awesome. If you haven't, caught up or you've missed a few, don't worry. Again, you can see it's all here. It's all here. You can watch it at your own pace, your own speed. Like we had a Halloween episode. Look at that. Halloween action. That was fun. We had a Thanksgiving thing going on. That was cool. We did a little, do we do other holiday one? No, I think those are the main themed ones. But you can see how the seasons have changed just by looking at the videos. Look, we started out as like tropical, moved into the fall. Now we're into the winter here. It's going to start looking like spring. We're going to have to change it up again. But we are on chapter 20, which is awesome because chapter 20, as you've heard or as you've seen probably just by looking over here at the top, is the final chapter of the book. So we're going to build a web server. We're going to use those muscles that we've been working on, right? We've been like building our Rust station action. We're going to do it today. So let's kick it off with the usual stuff and let's jump in. Let's talk about Rust a little bit. Feel free to ask questions in the chat. If you're watching on YouTube after the fact, not gonna lie, you probably missed out. It's okay though. You're catching it now. Put comments in at the bottom. It's always it's an evergreen party here, right? So the Twitter, follow there for updates. You're gonna see what we're doing after the book. Maybe we're gonna build some new stuff with Rust. Maybe we'll try out some other languages. I want to dive more into Rust though. I've been really enjoying it. So maybe we'll build some more programs with Rust. Let's see how the web server goes. The GitHub. It's all going to go here. This is the repo we've been working out of. All of the chapters are here. Feel free to check it out, pull it down, clone it, start your own thing, whatever. It's just here as a reference mostly for me, for the videos. For later when I want to go back. I also have the repo where we'll be coding out of for the video, but it's there if you need it. I don't think many people have needed it, but oh, you can't even see it. It's there if you need it. Look at this. There if you need it. Twitter's there if you need it. But today, if you've been watching, you know how we start out every week with a shout out to Steve Klobnik, Carol Nichols, and anyone from the Rust community who's contributed to this book. We have had an awesome time. I've definitely had an awesome time going through this book, and I can tell by some of the comments on YouTube, a few of you have also had an awesome time. It's been a lot of fun. So if you've been joining, thank you for coming along that journey. It's made it a lot easier. I usually have a tough time making it through technical books like this without wanting to jump in and write some code. I think for this language, I think it was the right move. And thank you to anyone who I talked to prior to doing this about, suggesting that we go through the book first. So we did all of it, but again, we couldn't have done it without Steve Klobnik, Carol Nichols, and anyone who contributed to this. So huge shout out again. I'll be sending out a tweet to thank them after this as well. Really, really awesome. I mean, this is like an amazing resource, and the fact that it's free is tremendous, and it speaks volumes to the types of people that we have in the Rust community here who are using this language and giving back to everybody else so that they can learn it. They're obviously passionate about it, and it shows in the work that they've done here with this book. So without further ado, we are diving into chapter 20. What's it all about? So you can see here, each chapter has been about a particular subject, right? We've done pretty much everything there is to do, right? all the foundational stuff, right? So we learned about threads, we've learned about reference counting, we've learned about box, we've learned about concurrency, we've learned about crates, we've learned about modules, we've learned about binary crates, library crates, we did functional programming, we did object-oriented concepts, we've done structs, we've done types. All that stuff has been great to give us a foundation, and now it's time for us to use that. And we did a little bit of usage with Rustlings, but again, Rustlings were also geared towards teaching. It's going to be really cool to see how to build something. And I know for this one, we're going to be building something from scratch. We're not going to be using a lot of crates. But as we get into real programs, we're going to be looking at crates more and pulling in crates. So I'm excited to see what it's like to build a real Rust program, and not just one that's designed to be a educational tool. So what is this all about? I got my orange juice here. Celebratory orange juice. Yeah, no, that's not what that is. All right, let's jump in. We'll start out with the book, and we will pull up the code as soon as we need to. Chapter 20, baby. Ooh, I'm ready. All right, ready? Let's see if we can try to get like a little epic narrative here. Ready? It's been a long journey, but we've reached the end of the book. In this chapter, we'll build one more project together to demonstrate some of the concepts we've covered in the final chapters, as well as recap some earlier lessons. For our final project, we'll make a web server that says hello and looks like figure 21 in a web browser. Wow, that's profound. I'm getting chills. Look at this program. Woo! No, it's not about the feature. It's not about what the program does. Hello. Albert in the chat says hello. It's not about what the program does. It's about what we're going to experience, right? It's the journey. It's not about the destination. It's about the journey, right? And that's, I think, I might get teary. I might get teary towards the end because it's really been a journey, right? This is the destination, but really it's been a journey. All right. Anyway, here is the plan to build the web server. We're going to learn a little bit about TCP and HTTP. For those of you not familiar with this, it's going to be really cool. I recently did an Elixir course. Well, I did it 2 years ago, and I did it again recently. And it dives into these concepts. But prior to that, I had a very limited understanding. Obviously, I was using this stuff day to day, but had a very little understanding of what TCP was behind the scenes and how HTTP built on top of it. So they give a little brief introduction to that, but definitely something cool to check out if you're interested in the concepts. So we're going to listen for TCP connections. So we're going to listen for when people connect to the server. We're going to parse a small number of HTTP requests, create a response. We'll start out with like a basic response, then maybe build, I guess, some HTML, and that's why we have that little HTML there. And then we're going to improve it by making it multi-threaded. So at first we're going to handle a single connection at a time, one at a time, and then we're going to make it multi-threaded. So as more than one connections connect, it'll actually handle them in parallel, which is how most web servers actually work, which is kind of cool. Obviously, right? Otherwise, if you went to a website, you'd have to wait in line with everybody else. Okay, before we get started, we should mention one detail. And this has been like, we've seen this a few times. It's basically saying like, this isn't the best way to build a web server. This is an educational endeavor, right? So let me move this out of the way so you can see. So this isn't the best way to build a web server. This is an educational endeavor. And so there's obviously crates we could use to do this for a production ready application. This is just going to be for us to learn. In this chapter, we want to learn not to take the easy route, right? That's the whole point here. Because Rust is a systems programming language, we can choose the level of abstraction we want to work with and can go to a lower level than is possible or practical in other languages, right? If you write a web server in Node, Python, Elixir, Ruby, Go, maybe less Go, but Java, they're going to be higher level abstractions. We're going to go a little lower level. That's the whole point of this, using a systems programming language, and part of the reason why we learned it. So we'll write the basic HTTP server and thread pool manually so that we can learn the general ideas and techniques behind the crates you might use in the future. Again, learning exercise, but it's going to be awesome. And I think that's why after this, I'm excited to do some more kind of coming up with our own projects, because it's going to force us to like look for crates, like literally Google for crates, similar to what we do in other languages, right? Like if you're implementing OAuth, God help you. Albert knows what I'm talking about in the chat. But if you're implementing, you would Google. You'd be like, all right, what are the OAuth libraries for my, particular language? Or maybe you're implementing routing, right? You would go and Google it. So yeah, it's a trap. Don't do it. The momentum killer. But yeah, so that's what we'll do. We'll look up some crates. But for now, we're going to go and build it from scratch. All right, let's jump in. So we're going to start out with a single-threaded web server. Before we begin, let's look at a quick overview of the protocols involved in building web servers. These details of these protocols are beyond the scope of this book, but a brief overview will give you the information you need. So, two main protocols involved in web servers are the HTTP protocol, Hypertext Transfer Protocol, that's where the two T's come from, and the Transmission Control Protocol, known as TCP. Both are request response, meaning you give a request, you get a response. The client initiates the request, the server gives you the response. But the content is different between the two protocols. TCP is a lower level protocol that describes the details of how information goes from one server to another, but it doesn't specify what the information that is being sent is. HTTP is built on top of that, and it does add that specification. So it's technically possible to use HTTP with other protocols, but in the vast majority of cases, HTTP sends its data over TCP. We'll work with the raw bytes of TCP and HTTP requests and responses. All right, so our web server needs to listen to a TCP connection. So that's the first part we'll work on. All right, I'm excited. The standard library offers a standard net module that lets us do this. Net for networking, obviously not for nets. Although we could use nets to catch crabs, but I think we're crab friendly now. Yes, in the chat, we're not gonna. That's a good question. Like I didn't think about that. Are we gonna still eat crabs after this? Is that weird? Is that cannibalism? I don't know. I honestly don't. These are the tough questions. I don't know these. But anyway, net in this case is network. So it lets us do this. Let's make a new project in the usual fashion. All right. So what I'm gonna do for this is what I always do. Nothing special. I faked you out. You sound like I was gonna do something cool. I'm not. What I'm going to do is I am going to move to the top right to get out of your way a little bit. And I get a little smaller. And I'm going to create a new project for this. We're going to call it Chapter 20. So let's just do this. Hold on. Let me just go here. Let's get rid of that. Okay, so we can make that a little smaller, right? Is that too small? We'll do that. All right, so here we're going to go to projects. We have all our chapters. I'm going to make a directory called Chapter 19 or Chapter 20 web server, and then in here I'm going to do let me go into it first. Chapter 20, and then I'm going to do cargo new hello, and we're building a binary crate, right? So it's not a library crate, and it tells you creating binary application. And what I'm going to do is I'm just going to go ahead and open directly to hello. This way I get the benefits of our Rust analyzer here. All right, also let me close out some of my I think we're good. Okay. Let me move here now. And I think that's a little big, right? Let's try to go one level lower. Okay. All right. So first things first, we created the Hello project. Now we are inside the Hello project. Does it say that we're in? Yeah, okay. Hello, there it is. Okay. Now enter the code below to start. So we're going to start. Let's do. This is it. This is the first code in our final project. Let's do it. So we're going to enter the code below, and what it's going to do, it's going to listen for the address 127.0.0.1. That may look familiar if you've done programming before, if you've built servers before. That is localhost, right? So you have your etc/host file if you're on a Mac. That maps to the word localhost maps to that. So localhost, that's what we're talking about there. And then the port 7878, which is going to, you can have many ports on localhost, right? So this is the one we're going to use. All right, so let's start out. And again, they mentioned, that might be a little small. Let's go a little bigger. You know what we'll do? We'll go a little bigger there, and we'll go a little bit shorter here. We can always zoom in and out. Yeah, let's go bigger, and we can always zoom out. Okay. So first we're going to pull in use standard. We're going to quickly run out of space. We're going smaller. Net and TCP listener. All right. In our main function, we're going to go ahead and do let listener. We're just copying what we see on the right there. Equal TCP listener. And we're going to do dot bind, which I think because we bind to a port generally, we're going to bind 127.0.0.1 : and this is the port 7878, And then this must return a result because I see we're doing an unwrap. And if I look at this, we can see right here, if you look at my Rust analyzer, it does in fact return a result. So we're going to just unwrap it, meaning if it fails, it'll panic, right? That's what unwrap does, right? It's going to try to get the thing. If it fails, it'll panic. If it succeeds, it'll give you the value. All right, perfect. Now, we're going to have a little loop for stream in listener. And so we're going to grab an iterator from listener, it looks like, incoming. So incoming should return an iterator. So, yep, so see here on the, if you can see the documentation, it might be a little grainy, but it says returns an iterator over the connections being received on the listener. The return iterator will never return none and will also not yield the peer's socket address. Not sure what this means, but the key thing is it's returning an iterator, which is going to allow us to leverage the loop. That's going to let us loop. And we're going to do let stream equals stream.unwrap. Again, this must return a result. And yes, so stream is a result of either a TCP stream, so you're either going to have the value, or an error. When we call unwrapped, once again, if it ends up being an error, it will panic, right? We could also handle this explicitly with a match expression, right? We could match on this and handle it, but we're just going to use unwrap because we want it to panic if it fails, apparently. And then what we're going to do is we're going to print a new line. We're going to print connection established. All right. Okay, let's read the description of what's going on here. So using TCP listener, we can listen for TCP connections at the address localhost 7878. In the address, this section before the colon is the IP address representing your computer. This is the same on every computer and doesn't represent the author's computer specifically. And 7878 is the port. We've chosen the port for two reasons. HTTP is normally accepted on this port, okay? And 7878 is Rust typed on a telephone. Yo, low key, yo, that's pretty cool. It's pretty cool. The bind function in this scenario works like the new function in that it will return a new TCP listener. So similar to like string : new. But the reason it's called bind is that a networking connecting to a port to listen to it is known as binding to a port. So that's why it's called bind. You're binding to a port, and it's this one right here. So the bind function, which we've talked about this, it returns a result. So it might fail. And so we want to call unwrap on it and have it panic if it fails. It returns a result because connecting to a port 80, so an example of how it could fail, connecting to port 80 requires administrator privileges. Non-administrators can listen only on ports higher than 1023. So if we try to connect to port 80 without being an admin, binding wouldn't work. Another example, binding wouldn't work if we ran two instances of our program both trying to bind to the same port. All right, so we won't worry about handling errors. Instead, we'll use unwrap to stop the program if the errors happen. Again, it will panic, right? And you can see here, if I hover over unwrap, you see right there, it says that it panics. So that's pretty cool. Panics if the value error with a panic message provided. Awesome. Okay, so the incoming method on TCP listener returns an iterator that gives us a sequence of streams, more specifically streams of type TCP stream. That is this part here, right? Let me zoom in a little bit there. So this here, we get TCP stream. A single stream represents an open connection between the client, right? The client and the server. We're writing the server part right now. So it represents an open connection between the client and the server. The server generates a response and the server closes the connection. As such, TCP stream will read from itself to see what the client sent and then allow us to write our response to the stream. Overall, this for loop will process each connection in turn and produce a series of streams for us to handle. Right now, we're not doing anything with the stream. We're literally just printing, right? And that's why we have the yellow underline, because it's going to tell us that it's not being used, right? All right. For now, our handling of the stream consists of calling unwrap to terminate our program if the stream has any errors. If there aren't any errors, the program prints a message. We'll add more functionality for the success case in the next listing. The reason we might receive errors from the incoming method when a client connects to the server is that we're not actually iterating over connections. Instead, we're iterating over connection attempts. So it might fail because we're trying to connect. It's a connection attempt, right? The connection might not be successful for a number of reasons. Many of them are operating system specific reasons. For example, many operating systems have a limit to the number of simultaneous open connections that it can support. New connection attempts beyond that number will produce an error until some of the open connections are closed. All right, that's reasonable, right? There's a limit. That's reasonable. Let's try running the code. So we're going to run cargo run and see what happens. Cargo run. All right, so our code is running. And now we're going to go to a browser. And we're going to try to go to that port in the browser. So we have a browser here. So I'm just going to go here. And there you go. Connection established. And you can see it called it a few times. That's probably because my browser is trying to reconnect. And you notice I use the localhost alias here, but I could also just do 127.0.0.1. That's going to be equivalent. So you can see it's trying to connect a few times, and that's probably just the work of the browser. Also, the browser, when you go to a website, requests a few different things, right? It requests the actual route, but it also tries to request a few other things, such as the favicon, so it can show it in the top right here. And it tries to request the robots.txt. There's a few things that it's actually trying to request, which may be the reason for seeing some of that there. And I think so connection reset because the server isn't currently sending back any data. When you look at your terminal, you should see several messages, or sometimes, so we see these several messages here. So I'm just going to stop the server. Sometimes you'll see multiple messages. We talked about this because the browser requests a few different things, right? It could also be the browser's trying to reconnect. The server isn't responding with any data, so it's going to keep trying to reconnect. When stream goes out of scope and is dropped at the end of the loop, so that's here. Stream goes out of scope here, right? After this loop. So like right here, it's out of scope. So when stream goes out of scope and is dropped at the end of the loop, the connection is closed as part of the drop implementation. Browsers sometimes deal with closed connections by retrying, and I think we saw that with our browser because the problem might be temporary. The important factor is that we've successfully gotten a handle on a TCP connection. Pretty sweet. Then it just says to, remember to stop the program, right? All right, reading the request. So now we're going to actually take that request, read some information off of it, and then do something, right? Excuse me. All right. Reading the request from the browser. To separate the concerns of first getting a connection and then taking some action with the connection, we'll start a new function for processing connections. In this new handle connection function, we'll read data from the TCP stream and print it so we can see the data being sent from the browser. All right, so let's do that. So zoom out here. Okay, so we're going to create a new function called handle connection. It's going to take a mutable stream, which I'm sure we'll figure out why. TCP stream. And we're going to create a mutable buffer, which I'm sure is going to be handling the actual request size. But we'll see. 0, 1024. Stream. So we're taking a stream in, and we're going to do stream.read, and we're going to pass it the mutable buffer. We're going to call unwrap, so that must return a result. And then we're going to print request string from UTF-8 lossy, and then we're passing it the reference to buffer. All right, let's see what's going on here. This looks a little confusing. And let's also see, so for TCP stream, we had to import some stuff here. So we're going to pull in standard IO prelude. So use standard IO prelude, pull in everything from there. And then we're going to pull in use standard nets. And again, we don't need to do 2 lines for this. We can do TCP listener, comma, TCP stream, right? That's the shorthand. And I think it looks a lot nicer. Okay, let's see what's going on. So we bring in the prelude into scope to get access to certain traits that let us read from and write to the stream. In the for loop in the main function, instead of printing a message that says we made a connection, we now call the handle connection function and pass that stream to it, right? So we're going to get our stream here, and now we need to call handle connection and pass our stream to it. So we call handle connection, we pass our stream. And again, it accepts a mutable stream, which means stream by default is probably going to be okay here. So we're just going to go ahead and do that. Perfect. So in the handle connection function, we made the stream parameter mutable. The reason is that the TCP stream instance keeps track of what data is returned to us internally. It might read more data when we ask for and save the data for the next time we ask for data. It therefore needs to be mutable because its internal state might change. Usually we think of reading as not needing mutation, right? But in this case, we need the mute keyword. All right. Next, we'll actually read from the stream. We do this in 2 steps. First, we declare a buffer on the stack to hold the data that is read in. That's happening right here. So we're let me zoom in there. We're declaring a buffer to hold the data, right? Let me actually, is that too small? No, it's too big. All right. So that holds the data we read in. We've made the buffer 1024 bytes in size, which is big enough to hold the data of a basic request and sufficient for our purposes in this chapter. So this is the size, right? If we wanted to handle requests of an arbitrary size, buffer management would need to be more complicated. We'll keep it simple for now. We'll pass the buffer to stream read, so we pass it there, which will read bytes from the TCP stream and then put them into the buffer. Okay, so read, if we look at the description of read takes a buffer, you can see there buff at mute. So pull some bytes from the source into the specified buffer, returning how many bytes were read. Okay. Second, we convert the bytes in the buffer to a string and print that string. That must be this part here. The string from UTF-8 lossy function takes a reference to a vector of unsigned 8-bit integers and produces a string from it. The lossy part of the name indicates the behavior of this function when it sees an invalid UTF-8 sequence. It will replace the invalid sequence with the question mark or the unknown replacement character. You might see replacement characters for characters in the buffer that aren't filled by request data. Okay, let's try this code. Start the program and make a request in a web browser again. Note that we'll still get an error page in the browser, but our program's output in the terminal will now look similar to this. All right, let's try it first before we take a look. So let's go on the top right. Let me get out of your way. Let's run cargo run. All right, we're running. Let's open up our browser. Ooh, check it out. That's pretty sweet. This may look familiar if you've used the developer tools. In fact, here, check it out. Check it out. Right? Let's zoom out a little bit. This is huge, right? Okay, let's look. So what do we have here? We have our request. This is the method, get, right? This is the protocol. This is where we're trying to go. This is the cache control. So these are the headers, right? The user agent. So that's what made the request. Accept encoding. So these are the types of things we accept as a response. We accept gzip, things like that. The language, right? So it's pretty cool. This is showing that request. And it actually looks very similar to what we see here. Except you can see we have connection keep alive, connection encoding, user agent, right? Request URL, refer proxy. So a lot of that stuff is coming from our headers here. So there's our accept, see, text HTML, application. That's all here as well, right here. So that's just our request. Pretty cool. And I'm just going to go ahead and close that and stop this. And we'll go back here. So that's pretty awesome. I don't see this. I'm not seeing those characters. But that might be okay. I don't know why. I guess we'll see. Depending on your browser, you might get a slightly different output. Now that we're printing the request data, we can see why we get multiple connections from one browser request by looking at the path after request get. If the repeated requests are requesting /, we know the browser is trying to fetch repeatedly because it's not getting a response from the program. Cool. All right, that's pretty, makes sense, right? Let's break down this request data to understand what the browser is asking of our program. All right, a closer look at the HTTP request. So this might be a recap for some of you that have dealt with this, but let's do it anyway. HTTP is a text-based protocol, and a request takes this format. You have your method, your request URI, HTTP version, your headers, and your body. The first line is the request line that holds information about what the client is requesting. So the first part of the request line that indicates the method being used. So it could be get, post, put, delete, whatever. It describes what they're trying to do. We sometimes call that the verb. Our client is using a get request. The next part of the request line is the slash, which indicates the uniform resource identifier, or the URI, if you've heard of URL, right? Similar, right? The URI is what the client's requesting from, right? What the resource is, we can think of it as. It's almost, but not quite the same as uniform resource locator, URL. The difference between URIs and URLs isn't important for our purpose of this chapter, but the HTTP spec uses the term URI, so we can just mentally substitute URL for URI here. Fine. The last part of the HTTP version the client uses, and then the request line ends in a CRLF sequence. CRLF stands for carriage, return, and line feed. Think about a typewriter, right? It says right here, which are the terms for the typewriter days. The carriage, return, line feed sequence can also be written as /r/n, where /r is a carriage return and /n is a line feed. The carriage, return, line feed sequence separates the request line from the rest of the data. Note that when the carriage, return, line feed is printed, we see a new line start rather than /r/n. All right. Ooh. Looking at the request line data we receive from running our program so far, we see that get is the method and the request URI is HTTP 1.1. Slash is the request URI and HTTP 1 is the version. After the request line, the remaining lines start from host onward are the headers. So we have headers and then the body. Try making a request from your browser to a different resource, right? So we can do /test. So let's do that. Let's do localhost. First, we'll start this up. I'll get out of the way. And let's do localhost 7878/Twitch. And you can see here, there's our request, right? Pretty cool. Oh, sorry, I went into the wrong. That's what I went to, /Twitch, and you can see there. So pretty cool. Nothing new if you've dealt with these things, but hey, we're building ourselves, which is pretty sweet. Okay, now we'll implement writing the response. So we're going to implement sending data in response to a client request. Responses have the following format: HTTP version, status code, reason phrase, and carriage return line feed. Then as the headers, another carriage return line feed, and the message body. Now, you notice there's no method. That's because the response doesn't need a method. The request has the method. The response just responds. The first line is a status line that contains the HTTP version used in the response, a numeric status code that summarizes the result of the request. The status code, right? We're talking like, if you've seen these, 200, that's the OK. 404, resource can't be found. 403, forbidden, right? 401, invalid request. Maybe you got a 302, a redirect. Maybe a 5, yeah. I'm name dropping some status codes. I know them. All right, I'm familiar. I'm allowed to name drop them. Cool, okay? Please. But I know my status codes. All right, but anyway. And then the reason phrase, right? So why? That's the reason that goes with the status code. So okay for 200, again, name dropping. 500, right? Service error. Maybe we'll get a 401, invalid request. Maybe we'll get, what is teapot? 4 something? 420 is teapot? I forget. Who knows? But that's it. And then carriage return, and then the body. The body is the response body, right? So that's what you're going to get back. Here's an example response that uses HTTP version 1.1, has a status code of 200, an OK reason phrase, no headers, and no body. Why? How do you know there's no headers, no body? Because you see your CRLF, carriage return line feed, CRLF, right? Nothing in between. The status code 200 is a standard successful response. The text is a tiny successful HTTP response. Let's write this into the stream as our response to a successful request from the handle connection function. So we're going to remove the print line that was printing the request data and replace it with the code below. All right, let's try it out. So we're going to get rid of this. We're going to keep our stream read, but we're going to go ahead and create a response. Let response equal, and this is our response text, HTTP. This is the version 1.1. Again, this is the response code 200. OK, which is the description basically of the code. Then carriage return line feed. Right, that's the carriage return line feed. Carriage return line feed. And that's it. Now what are we going to do with the response? Well, we're going to do stream.write, apparently. We're going to pass it response.asBytes. And it looks like this can fail, so it returns a result. So we're going to go ahead and unwrap that. Normally, we'd probably want to handle those errors, but for now, we're just going to go ahead and panic if that fails. Then we're going to try to do stream.flush, which again can also fail. Flush the output stream, ensuring that all intermediate buffered contents reach their destination. Errors. It's considered an error if not all bytes could be written due to I/O errors or end of file being reached. So that's why we need to go ahead and include an unwrap there as well. All right, so we defined our response. We defined, we call asBytes on our response to convert the string data to bytes. The write method on the stream takes a reference to a vector of unsigned 8-bit integers and sends those bytes directly down the connection. Because the operation can fail, we use unwrap. Again, in a real application, you would have to have error handling. And finally, flush will wait and prevent the program from continuing until all bytes are written to the connection. TCP stream contains an internal buffer to minimize calls to the underlying operating system. Pretty cool. With these changes, let's run our code and make a request. We're no longer printing any data to the terminal, so we won't see any output in the output from cargo, but we can check the browser, right? You should get a blank page instead of an error. And we can look at we'll look at the response from the browser tab. All right, so I'm going to go ahead and run this. I'm going to go top right. I can't get tired. It's the final chapter. I'm going to chug some water. All right. Let's go ahead and run cargo run. We're running. I'm going to open up the dev tools here. Put those here. Let's make those smaller. There, you can see that. Yep. And we're going to go ahead and refresh. And we got a blank page. And let's go ahead and look at what we got as our response. So here's our response, right? Check this out. We can look at the preview. We didn't send any data, but here, check out the response. We got a status code of 200 and okay. And you can look down here. There's no response headers, nothing like that, because we didn't send anything. The response is empty. There's no response data, but we did get our 200 and we got our okay. And the same thing, we responded the same thing for the favicon. We didn't return an image, we just returned the 200 response. So all good, pretty cool. We're building a web server. All right. We just hand coded an HTTP request and response. If you've never done that, I remember like I've only recently hand coded. I mean, this is the first time I did it in Rust, but I only recently hand coded a TCP HTTP response and request. It's pretty cool. So, I mean, I think it's fun. I think it's a fun thing to do. Usually, obviously, we have abstractions for this stuff, but it's cool to kind of see how that works. So that's awesome. All right. Next up, let me move this over here. Okay, we're going to return some HTML, and we're going to return that hello, right? Remember? So let's implement the functionality for returning more than a blank page. Yo, maybe we'll get fun with it. Let's get fun with it. Let's get a little fun with it. Let's add some styling. We'll do it inline, whatever. Nobody's going to care. No one's looking. This isn't front end. We're adding some inline styling. Nobody cares. All right. Anyway, we're going to create a new file called hello.html in the root of our project directory, not the source directory. You can input any HTML you want. It knows we're going to get funky with it. We're going to get funky with it. All right. So where are we putting it? Where does it want us to put it? It wants us to put it in the root. Put it out here. We're going to call it hello.html. We're going to start it out. We're going to give it the old doc type. We're going to give it HTML. We're going to give it, we'll do the meta. We'll do the whole thing. Char set, right? UTF-8. Classic. We'll give it a title. We'll call it hello Twitch, and we're gonna call it hello Rustations. We're united. We're Rustations United Front. Did I even spell that right? All right. That's gonna be in our head, right? All right. So now we got that. Now let's create a body here. What do they got in there? It's body H1. We're gonna say hello stations. We're gonna do a paragraph here. Welcome to the Learn Rust live stream. All right. What are we gonna do? What are we gonna do? We're gonna do little styles. We're gonna do style. We're just do a little quick one, right? We're gonna do height equals view height, width equals view width. We're gonna copy that to our body. We're gonna do background color. What color are we doing? We're doing tomato, my favorite. Gotta do tomato. What are we gonna do here? We're gonna do a color on the text. We're gonna go with white so you can see it on that tomato background. All right. We can preview this in the browser if we want, but let's wait. Let's wait a little bit. So this is a minimal HTML5 document with a heading and some text. To return this from the server when a request is received, we'll modify handle connection as shown below to read the HTML file, add it to the response body, and send it. Yo, I'm excited for this. Let's try it. Let's try it. All right, so how do we do this? So we got our mutable buffer. Now we're gonna read that file. So we're gonna do stream. Oh, no, wait. So we're gonna stream that. We're gonna do it right here. So let contents, so this is the contents of our file, equal file system, and we need to import file system. So import file system. We've used file system before. This isn't anything new. File system read to string. It returns a result, so we're gonna unwrap that. What are we gonna read? We're gonna read the file. So it's gonna use the path from where we are right now, right from our root. So our file is at hello.html. And again, it returns a result. So we can either match on it or we can unwrap it. What we might wanna do is we could, for example, if let's say we had routing, right? We can match and see like what the route is and return a different thing per route. But for now, we just have a single route. So we're gonna go ahead and grab the contents of that file, unwrap it. Now let's see, this is a little bit different. So here we're doing response equals format. We're using the format macro. We know it's a macro because the exclamation point, right? It's one of the macro rules macros that we learned about. We have our HTTP 1.0 OK/R/N, so that's our carriage return. We're going to include content length. So this is the headers. Remember, these are the headers. Content length is a header. We have a carriage return. Looks like we're doing another carriage return. And then we're going to template in some data. All right, let's try it. What are we going to template in? Well, first let's move that there. We're going to template in contents.len. So the length of the content. That makes sense. That's going to go into the content length. Duh. So we're going to template in, basically what we're saying is we're going to template in here the actual content length, how much, what the content length of that HTML file is, and then we'll template in the content itself as the body. So we're going to do contents.len followed by contents. This part looks like it stays the same. And let's see. So we've added a line at the top to bring the standard library's file system module into scope. The code for reading the contents of a file to a string should look familiar. We used it in chapter 12 when we read the contents of a file for our IO project. Next, we're going to use the format macro to add the file's contents as the body of the success response. To ensure valid HTTP response, we add the content length header. which is set to the size of our response body. In this case, it's the size of our hello.html file. Run this code with cargo run and load in the browser, and we should see our HTML. All right, let's see. This is pretty cool. I'm excited. I hope it works, and I hope we get our cool HTML. All right, so let's go top right here. Let's clear it out. Let's go cargo run. Our server's running. Let's go over here. Whoo! Look at that. Wow. Pretty cool, right? We built a little web server without using libraries. That's pretty awesome. And it's honestly not that much code. And for Rust, that's a lot. Well, hello, Rust stations. Welcome to the Learn Rust live stream. Pretty cool, right? I think so. And we're using our nice styling. So we got our background, our full tomato colored background. It's looking pretty good. Nice tomato light shining upon my face. I like it. Okay, that's awesome. Currently, we're ignoring the request data in buffer and just sending back the contents of the HTML file unconditionally. Right. I sent test. I can send different paths. We're just sending it back no matter what. This means if you try requesting something else, which we did, we actually requested /Twitch, you'll see you still get back the same HTML response. Our server is very limited and is not what most web servers do. We want to customize our responses depending on the request and only send back the HTML for a well-formed request /. Okay, so now we want to make sure we only send it when it's a request /. Validating the request and selectively responding. Right now, our web server returns the HTML file returns the HTML in the file no matter what the client requested. Let's add functionality to check that the browser is requesting / before returning the HTML file and return an error if the browser requests anything else. For this, we need to modify our handle connection function like we have below. The new code checks the content of the request received against what we know a request for / looks like and adds if and else blocks to treat requests differently. All right, let's try it. So what is the same here? So we know some of the stuff's the same. Let me go down here. Actually, I'll stay up here. I'm out of your way, right? Cool. So what do we know is the same? So this buffer part is the same. That's the same. We're going to have get. So basically, what we're going to do here is we're going to define what we know a proper request to / looks like, right? So we're going to do let get equal get /http /1.1 carriage return new line. I don't know what that B does in the beginning. Oh, the bytes. Okay. Yeah, so it gets it as a reference. It basically gives me a vector of unsigned 8-bit integers. So that's what it's going to do there. All right. Now we're going to do a check. If buffer, oh cool, if buffer.starts with, and we're going to check that it starts with get, then we're going to do this stuff, right? We're going to give it this. Pretty cool, pretty cool. I don't know why my indent's not doing anything. Can I format? Weird. All right, let's just indent this. There we go. All right, so if it starts with get, we do that. Otherwise, we're going to do something else. Otherwise, we have some other request. First, we hardcode the data corresponding to the / request into the get variable. Because we're reading raw bytes into the buffer, we transform get into a byte string by adding the B in front. Byte string syntax at the start of the data. Then we check whether buffer starts with the bytes in get. If it does, it means we've received a well-formed request. So /, which is the success case we'll handle in the if block, and returns the contents of the HTML file. If buffer does not start with the bytes in get, it means we've received some other request. We'll add code in the else block in a moment to respond to all other requests. So we run this code and make a request to 7878 at the /, we should get the HTML. If we make any other request, you'll get a connection error like those you saw when running the code in the listing below. All right, let's try it. Clear, cargo run. Is it going to let me do anything with the empty else? I guess it will. All right, so let's go to 7878. That worked. Now let's go to /Twitch. And you can see here, it's still loading. While it is showing me, it is showing this page, we can actually look at the network and we can see that if I go to /Twitch, it's failing. So that's exactly what we want, right? Perfect. All right. Now let's add the code below in the else block to return a response with the status code of 404, which is technically, or it is the status code you return when something can't be found, or resource can't be found, right? Many of you have probably seen this. Maybe you've been to GitHub and you've accidentally got to a 404 page where you weren't signed in, and you saw the Octocat dressed as a Jedi telling you this isn't the page you're looking for. Or maybe I'm sure you've come across a 404. Everyone probably has, going on the internet, clicking an old link. Sometimes you'll end up with a 404. Anyway, we're going to go ahead and return a 404 in this else block. So let's do that here. So what are we going to return? We're going to create a new HTML file called 404.html. For now, what we're going to do is let's write the code that they have here. So let status line. And so it's going to be basically our response, right? The status line is that first portion there. And since we're not returning any content, we don't need to have the same kind of formatting going on that we have here. So we're just going to do HTTP, that's the version, /1.1. We're going to give it a 404, which is not found. And we're going to do /r/n/r/n. And we're going to do let contents equal. We're going to read the 404 file, which we have yet to create. 404.html. And again, that could fail, so we're going to unwrap that. And I'm sure we'll maybe, to remove code duplication, we'll probably abstract some of this. But basically, we're just going to copy what we have here. So here we're going to do, well, first we're going to do this. And we're going to go ahead and do let response equal format. Here we're using that macro. We have our first line and our second line. And so our status line goes first. And we could have done this all in one line, but they're just breaking it up. And we can do this. All right. So let's go ahead and write that 404 page. So what we'll do is we'll copy our hello HTML and we'll rename it. Well, first we'll move it out. Okay, we'll rename it first. 404. Now we'll move it out here. And let's change it. So the title will be Hello REST Stations, but this title here will be Oops. We can't find the page you are looking for. And then we'll say, let's do this. Let's say, let's give them a link to go back home. Return to home screen. And what is that going to do? It's going to have an href, and we're just going to link them back to /. Right? Give them away back. And let's change the color. Let's go with my other favorite color. So if you've worked with me before, you know my two favorite colors are this kind of tomatoey orange color and an aqua color. So let's go with aqua. Or maybe something darker. Maybe we can do turquoise. Teal. I like teal. Let's go with teal. All right. Now let's go ahead and start our server here. Oh, it started already, but let's go ahead and stop it. Let's cargo run it. Let's go over here. Let's go to / first. All good in the neighborhood. Let's go to /Twitch. Oops, can't find the page we're looking for. Return to home screen. Bam. Wow, look at this. Look at this. Let's try that again. / something else, right? Whatever it is, you can type anything, right? Something. Bam, we're taken to this page. We got our nice little link to take us right back. Pretty cool. Built a web server. Wow. We built a web server in Rust. Pretty cool. You could build, should we build my profile page? Should we build my portfolio site with this? No, the answer is no, probably not. Because we need to handle security, we'll probably use a crate for that, right? All right. Now, see, they're going to get us into the refactoring. I like that because I was going to say we're doing a lot of duplication. With these changes, we can see that everything works. That's basically what this says. A touch of refactoring. At the moment, the if and else blocks have a lot of repetition, right? They're both reading files and writing the contents of the files to the stream. The only differences are the status line and the file name. Let's make the code more concise by pulling out those differences into separate if and else lines that will assign the values of the status line and the file name to variables. We can then use those variables unconditionally, right, outside to read the file and write the response. So what we're going to do, that's awesome. We're going to return a tuple. So let's do that. Let's start out up here. So we'll do let, and so we're doing tuple destructuring, right? So we're going to say the status line, file name equals, and then the if is an expression, right? Remember, the if is an expression. So we can actually do buffer dot starts with get, and if it does, we're going to return a tuple, right? We want to first return the status line. Well, what's the status line? We know that here the status line is, oh, well, in this case, it's not actually, we're leaving off the content length. That's worth noting. We're abandoning the content length to make this work, which I find interesting. Pretty interesting. But anyway, let's go ahead and do that. But yeah, you can tell. So if you notice that we are no longer handling the content length, which is maybe not ideal, but it's, I think what they're trying to illustrate here is just what we do for refactoring. So here we can get rid of our content length because we want to make it very generic. And we only need the two carriage returns, right? So we can get rid of that other carriage return and get rid of that there as well. Okay, so there's our status line. And now what we'll do is we will have our file. So this is the file that it should go to. Hello.html. You see that there? All right, perfect. And otherwise, right, so if that's not the case, we're going to go with the return line here, which is our status line, followed by 404.html. All right, so what is that going to do? So depending on the conditional, it's going to return a tuple either way. It's either going to be this tuple or this tuple. That'll populate our status line and our file name, and then we'll just use those below down here. How are we going to use those? Let's get rid of these ifs. Let's get rid of this. We're going to say here contents equals, right? Oh, and this has to be like that. Contents equals file read to string, and we're going to use the file name here instead of this. And the response, instead of doing all of this, the response is basically just going to be format status line. And again, we need to do this, right? We pass the status line and then contents. Then we can just do business as usual. Stream.write, stream.flush. And here we need a semicolon. All right, let's try it. Cargo run. Refresh here. Hello Rust. We go to /Twitch. There we go. We go to /anything, right? / blah, 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 blah. Oops, can't find the page you're looking for. Return to home screen. Pretty cool. Awesome. All right, let's stop that. All right. Now that the if and else blocks only return the appropriate variables for status line and file name in a tuple, then we use destructuring on those two values to pull them out, right? The previous duplicated code is now outside the if and else blocks and uses the status and new line variables. This makes it easier to see the difference between the two cases, and it means we have only one place to update the code if we want to change how the file reading and responding writing works. The behavior of the code in listing 20-9 will be the same as in listing 20-8. Awesome. We now have a simple web server in approximately 40 lines of Rust code that responds to one request with a page of content and responds to all other requests with the 404 page. Hell yeah. Currently, our server runs in a single thread, meaning it can only serve one request at a time. Let's examine how that can be a problem by simulating some slow requests. Then we'll fix it so our server can handle multiple threads at once. All right. How you doing over there, chat? How you hanging in? It's quiet. It's quiet in the chat. You guys are all mesmerized by this web server. I know. I get it. I'm mesmerized too. It's pretty cool. All right. Albert says, doing well. Good, good. I'm glad. Hope you're enjoying the Rust. Turning our single-threaded server into a multi-threaded server. So let's talk about first why we might want to do this, right? If you have a single-threaded server, it can only handle one request at a time. Meaning, if you send multiple requests to it, it handles the first one and gets a response, then and only then will it handle the second and give it a response. So it would be like waiting in line to get a website. It would also wreck your server, right? If you have a popular website, it would destroy your server. So it would have to handle lots and lots of stuff. So in order to handle multiple simultaneous requests, we need to have multi-threading, right? We need to have a process to spawn up a process to handle the response so that you can handle more than one at once. And that's why we need more threads. Right now, the server will process each request in turn. So just what I just said. Meaning it won't process the second connection until the first connection has finished. If the server received more and more requests, the serial execution will be less and less optimal. If the server receives a request that takes a long time to process, subsequent requests will have to wait until the long request is finished, even if the new request can be processed quickly, right? We'll need to fix this, but first we'll look at the problem in action. All right, so let's try to simulate a slow request in the current server implementation. We'll look at how slow processing requests can affect other requests made by our current server implementation. Listing 2010 implements handling a request to sleep with a simulated slow response that will cause the server to sleep for 5 seconds before responding. All right. So let's go ahead and we're going to do a second request. So we'll add another possible option here called sleep. And it equals b get/sleep http. Same thing here, 1.1, carriage return, new line. All right, this part's the same. Let status line, blah, blah. We're gonna just add another else if block, right? So we do that here, else if buffer dot starts with sleep, of course. And if it starts with sleep, what are we gonna do? We are gonna thread sleep and then we'll return the tuple. So for our tuple, we will return the same thing, right? We'll return that, but first we're gonna go ahead and call thread, and we're gonna have to pull this in, I just realized too. So I'm just gonna pull in here, standard, we have file system, I'm gonna also pull in thread, and we're gonna pull in use standard time duration. All right, so that was down here that I was doing that, so we're gonna do thread sleep, and we're telling it to sleep for a little bit. How are we doing that? We're gonna use a duration. We've done this before, so this probably looks familiar. From seconds, 5 seconds is what we wanna do. And so now if we go to /sleep, it'll wait 5 seconds and then it'll respond with hello. Pretty cool. The code's a bit messy, but it's good enough to simulate for the simulation purposes. We create a second request sleep whose data our server recognizes. We added an else if after the if block to check if the request is to /sleep. When the request is received, the server will sleep for 5 seconds before rendering the successful HTML page. You can see how primitive our server is. Real libraries would handle the recognition of multiple requests in a much less verbose way, right? It's going to handle it much nicer. Start the server using cargo run, then open 2 browser windows, one for the regular /route and one for the /sleep route. If you enter the /URI a few times, as before, you'll see it respond quickly. But if you enter sleep and then load /, you'll see the / waits until sleep has slept for its full 5 seconds before loading. There are multiple ways we can change how our web server works to avoid having more requests back up behind a slow request. The one we'll implement is a thread pool. All right, let's try this. So here's how we're going to do it. We're going to have this one open here. I'm going to open a new one over here. Okay, I'm going to go to the bottom here. All right, we're going to go, we got slash here, and we're going to go to sleep here. Let's first test sleep. Ready? 1, 2, 3, 4, 5. Bam. Oh, can't reach. Did I not cargo run? Is that what happened? Was it a coincidence that it just waited 5 seconds? Probably. All right, cargo run. Let's go back. Let's go back. All right, ready? I'm going to refresh it. Ready? 1, 2, 3, 4, 5. Bam. If you didn't notice, it was loading here. Here, you know what? Let me do this. Let me go back. Let me go back. Let me go to like Google. Sure, whatever this is. All right, now let's go to localhost. Ready? Wow, that's slash. Slash was quick. We saw that. Okay, we see slash is quick here. Slash is very quick. Let's go to Google. Now let's go to slash sleep again. One, 2, 3, 4, 5. Bam. Right? Now, let's, again, you can see that sleep is fast. You can see it just, if I hit refresh, watch. Instant. Now, what I'm going to do, I'm going to refresh this, causing it to sleep, and then I'm going to refresh this and see that it does, in fact, take a little while. Ready? Actually, here's what we'll do. We'll go to the other route, and then we'll click the link and see how long it takes the link to load. Because, again, the link is going to bring you here. So, ready? I'm going to refresh this. It's going to cause it to sleep. What does that mean? It's going to take 5 seconds before it shows this page. In the meantime, we're also going to click this. Normally, this goes instantly. But what we're going to see is that it's going to not. It's going to wait. Ready? Refreshing. Look, it's blocking. See? This will finish, and then it goes. So there, we illustrated it. Also, check out how cool these colors look next to each other. Because they're inverses. If you look, I have a very similar color theme going on over here. I got the orange and the blue. That's like the main theme. That's like the whole flavor we got going on over here at the Tom McGraw house, you know? All right, so there we go. We've demonstrated the blocking. Pretty cool. Okay, now let's do something about it. All right. All right. What are we gonna do? What are we gonna do? First, let's close this. I'm gonna move back to your top right here. And let's see. So we saw that. So now we're gonna need a thread pool. Improving throughput with a thread pool. A thread pool, not to be confused with dead pool, is a group of spawn threads that are waiting and ready to handle a task. When the program receives a new task, it assigns one of the threads in the pool to a task, and that thread will process the task. The remaining threads in the pool are available to handle any other tasks that come in while the first thread is processed. So you have a thread pool, it's a bunch of threads hanging out, a bunch of people waiting, and then a request comes in and the thread pool think of it like this, right? Think of it like, this is a terrible analogy because no one enjoys this experience, but car dealership, right? You go to a car dealership, there's like a bunch of salesmen, like salespeople, like skulking around, and you go and one of them helps you, or you know, anywhere you go, right? One of them helps you, and there's a pool of them waiting around for the next person to come. I imagine they look like this. No, whatever. But any type of place, right? It's a thread pool. It's going to wait for the request and handle it, and hopefully there's enough threads to handle all the requests. Okay, we'll limit the number of threads in the pool to a small number to protect us from denial of service, aka DOS attacks. You've heard of DDoS. That just stands for deliberate denial of service. That means somebody is intentionally doing it. It is a malicious intent, usually. If we had our program create a new thread for each request as it came in, someone making 10 million requests to our server could create havoc by using up all of our server's resources and grinding the processing of a request to a halt. Rather than spawning unlimited threads, we'll have a fixed number of threads. So we'll have a fixed number of car salespeople to handle the incoming traffic. Could we think of something better than that? We probably can, right? Salespeople. Car sales is not fun. Think of it like something similar. The Apple Store. When you walk into the Apple Store, you want help. There's somebody there to help you. There's a limited number of employees. They can only help so many people at a given time. Anywhere, actually restaurant, anywhere, right? This works for everything. There's only a certain number of tables at a restaurant. Same deal. And you can come in at any time and there's a server that helps you. All right. I don't know why I went cars. Whatever. Okay. So we're not going to spawn unlimited threads. We'll maintain a queue of incoming requests, right? As requests come in, they'll be sent to the pool for processing. We'll maintain a queue of the incoming requests. That's going to be important. Each of the threads in the pool will pop off a request from this queue. So each of the threads will take a request off the queue, handle the request, and then ask the queue for another request. So if you think of a server will go to a table, serve the table, and then refill that table, try to get another table, right? Or if you're Apple Store, you'll help a customer, and then you'll ask, who else needs help, right? Maybe you're at the deli counter. Who else needs help? You take a number, right? Pops it off the queue. There you go. So many analogies here. Come on. With this design, we can process n requests concurrently, where n is the number of threads. If each thread is responding to a long-running request, subsequent requests can still back up in the queue, but we've increased the number of long-running requests we can handle before reaching that point. So we can handle n at a time, where n is equal to the number of threads. Got it. This technique is just one of many ways to improve the throughput of a web server. Other options you might explore are the fork join model and the single-threaded async IO model. That's like Node, right? If you're interested in this topic, you can read more about other solutions and try to implement them in Rust. With a low-level language like Rust, all of these options are possible. Pretty cool. Before we begin implementing a thread pool, let's talk about what using the pool would look like. When you're trying to design code, writing the client interface first can help guide your design. What do we mean by that? You write how you would like to use it before you build it. This way you know what specification you want to code to. All right. Write the API of the code so it's structured in a way you want to call it. Then implement the functionality within the structure rather than implementing the functionality and then designing the public API. Similar to how we use test-driven development in the project in Chapter 12, we'll use compiler-driven development here. We'll write the code that calls the functions we want, and then we'll look at the errors from the compiler to determine what we should change next to get the code to work. Okay, code structure. If we could spawn a thread for each request. First, let's explore how our code might look if it did create a new thread for every connection. As mentioned earlier, this isn't our final plan due to the problems with potentially spawning an unlimited number of threads, but it's a starting point. So the listing below shows the changes to make the main to spawn a new thread for each request. This is not with a thread pool. This is saying for every request, spawn a new thread, right? So what would that look like? So we'd have our listener, for stream and incoming, we'd spawn a new thread. So we'd unwrap, and instead of calling handle connection here, we'd call thread spawn, and again, we give it the closure, right? Handle connection. So again, this is one thread for every single request, right? And so we can see here, as you learned in Chapter 16, well, let's see what it says right away. It says, mismatched unit type, found struct join handle. Try adding a semicolon. Oh. There we go. So if we try this, let's just try it. If we try this with our little example here, if I go to localhost, so again, if I go here, it's instant. And remember, it was blocking before if I went to the sleep route. So I'm going to go to the sleep route here. But I'm going to return here, and it returns instantly because a new thread was spawned. Look at that. Look how cool that is. But again, the reason we don't want to do this, the reason we're not done, is because we've now opened ourselves to tying a request to a thread. That means anyone that can make requests, right? You can hammer our server with requests, you'll spawn. So it's almost like we're leaking a little too much power to the requester. So we want to limit those numbers. But that's pretty cool that we were able to do that already to fix that problem with just one change. The only change is we wrapped it in a thread spawn. But we need more control over that. Okay. If you run this code and load sleep in your browser, then slash in 2 more browser tabs, you'll indeed see the requests don't have to wait for sleep to finish. But as we mentioned, this will eventually overwhelm the system because you're making new threads every time, right? Creating a similar interface for a finite number of threads. We want our thread pool to work in a similar, familiar way, so switching from threads to a thread pool doesn't require a large change to the code that uses our API. So it shows a hypothetical interface for a thread pool struct we want to use instead of thread spawn. So we're writing how we would like to use it first before implementing it. I like that. So let's go here and let's do let pool equal thread pool new, and we're giving it the number of threads we want. So again, we haven't implemented this yet. This is going to be compiler-driven development. I really like this approach. And how are we going to use it? We're going to do, instead of pool.spawn, thread.spawn, we're going to do pool.execute. So it's going to give it, it's going to try to execute this code given the pool. What does that mean? Whatever's available in the pool will execute this code. We're going to code that after, but right now it's transparent to us. We don't care how it's implemented. That's an implementation detail. This is how we want to be able to use it. We just want to say, hey, someone in the pool, handle this. We'll use thread pool new to create a new thread pool with a configurable number of threads. In our case, we're going to go with 4. Then in the for loop, pool execute has a similar interface to thread spawn in that it takes a closure. The pool should run for each stream. We need to implement pool execute so it takes the closure and gives it to the thread in the pool to run, right? The code won't compile yet, but we'll try so the compiler can guide us on how to fix it. I love that. All right, so here's what we're going to do. Let's clear this out. Let's go ahead and I'll move this up out of your way here so we can see a little bit more of what's going on in our terminal. Let's run cargo check. All right, failed to resolve use of undeclared type or module thread pool. So it's saying we haven't defined thread pool, right? The error tells us we need a thread pool type or module, so we'll build one now. Our thread pool implementation will be independent of the kind of work our web server is doing. So let's switch the hello crate from a binary crate to a library crate to hold our thread pool implementation. After we change to a library crate, we could also use the separate thread pool library for any work we want to do using a thread pool, not just for serving web requests. So create a source lib that contains the following, which is the simplest definition of a thread pool. All right, so we're going to have a source lib. Now we have a library crate. And we're going to create just a basic struct for thread pool. All right. Then create a new directory, source bin, and move the binary crate rooted in source main into source bin main. Okay. So let's do that. Cool. Awesome. So we moved it there. After moving the main RS file, edit it to bring the library crate in and bring thread pool into scope by adding the following code to the top of the file. So we're going to do use hello thread pool. There we go. The code still won't work, but let's check it again to see what the error is. All right, so we're going to clear this out. We're going to do cargo check. Oh, cool. Look at this. It expects us to define the thread pool. Right now it's expecting where, right? So if we go to our lib, we can just make some changes here. Now let's see what it does, just for fun. So now it's associating a new function, right? We haven't defined a new function. So we know, I'm gonna jump ahead without looking, but we know we're gonna need implementation, thread pool, right? We're gonna need a function called new. What is our function gonna do? It's going to return a thread pool. Right, and what do we pass? Let's see what we pass new. We pass it a number, right? So we pass it a threads, which is a, we'll say it's a unsigned 8-bit integer, and it returns a thread pool. And and it's saying it does nothing, so we know we're gonna have to return thread pool. There we go. But let's look at what they want us to do, but just so we can see, and if we do now, if we do cargo check, we'll get some other error. Private function, because we didn't make it public. Now if we clear it, so this is kind of cool. I like using the compiler like this. It's pretty sweet. We're leaning on the compiler. And now we have the correct thing, but now execute is not defined. So pretty cool. We'll keep going. I think we could probably do it without, let's keep going. Let's keep going. Let's keep reading. Okay, so let me just go ahead and do this. All right, so the error indicates we need to create an associated function named new for the thread pool. We also know that new needs to have one parameter that can accept 4 as an argument and should return a thread pool instance. Let's implement the simplest function new. So, okay, so the difference is we're gonna say they're doing size and using a usize, which is probably much more idiomatic, right? Size, and they're using usize. And it returns a thread pool, so we just do thread pool. I think what we had was correct. So yeah, so now it says, oh, you know, we need this here. So now it says, if we run cargo check again, we're gonna see that it's looking for the execute. Yep. So now the error occurs because we don't have an execute method on thread pool. Recall from creating a similar interface for a finite number of threads section that we decided our thread pool should have an interface similar to thread spawn. In addition, we'll implement the execute function so it takes the closure it's given and gives it to the idle thread in the pool to run. Hell yeah. We'll define the execute method on thread pool to take a closure as a parameter. So recall from storing closures using generic parameters and the function traits section, function mute and function once. In chapter 13, that we can take a closure as parameters with 3 different traits: function mute, function once, and function. We'll need to decide which kind of closure to use here. We know we'll end up doing something similar to the standard library thread spawn implementation, so we can look at what bounds the signature of thread spawn has on its parameter. All right. The documentation shows us the following. Spawn, we have a function. The F-type parameter is the one we're concerned with here. The T-type parameter is related to the return value, and we're not concerned with that. We can see that spawn uses fn once as the trait bound on f, so that's what we're going to use. This is probably what we want to use as well, because we'll eventually pass the argument we get in execute to spawn. We can be further confident that f once is the trait we want to use because the thread for running a request will only execute the request closure one time, which matches the once in fn once. The F-type parameter also has the trait bound send and the lifetime bound static, which are useful in our situation. We need send to transfer the closure from one thread to another, and static because we don't know how long the thread will take to execute. Let's create an execute method on thread pool that will take a generic parameter of type F with these bounds. All right, let's do it. So we're going to create a function here, public function execute. That's going to take a generic F, the mutable self here, and then F, which is of type F, right? And then we're saying, where F is of type fn once, so we're just describing what it's allowed here, fn once plus send plus static lifetime, right? All right. And then we need to put some code. So this is just, I mean, you could, this could all be on the same line there. It's just, we're breaking it up to be clear. All right, we could do this here. All right. We still use the parentheses after fn once because this fn once represents a closure that takes no parameters and returns the unit type. Just like function definitions, the return type can be omitted from the signature, but even if we have no parameters, we still need the parentheses. Again, this is the simplest implementation of the execute method. It does nothing, but we're trying only to make our code compile. Let's check again. All right, let's check it. Oh, you can't see because I'm in your way here. Hold on. Let me move to your bottom left for a second. So you can see here, I just moved everything onto one line. That's all. All right, so you can see it compiled successfully at least. It compiles, but note that if you try cargo run and make a request in the browser, you'll see errors in the browser that we saw in the beginning of the chapter. Our library isn't actually calling the closure pass to execute yet. Note, a saying you might hear about languages with strict compilers, such as Haskell and Rust, is if the code compiles, it works. But this saying is not universally true. Our project compiles, but it does absolutely nothing. If we were building a real complete project, this would be a good time to start writing unit tests to check that the code compiles and has the actual behavior that we want, right? Validating the number of threads in new. We aren't doing anything in the parameters to new and execute. Let's implement the bodies of these functions with the behavior we want. To start, let's think about the new, right? Let's think about new. Earlier, we chose an unassigned type for the size parameter because a pool with a negative number of threads makes no sense, so it needs to be unsigned. However, a pool with 0 threads also makes no sense, yet 0 is a perfectly valid use size. We'll add code to check the size is greater than 0 before we return a thread pool instance and have the program panic if it receives a 0 using the assert macro. All right, let's do that. So in our implementation of thread pool, so I'll scroll this down a little bit. Let me move over here. Here's what I'll do. I'll move over here. All right, so we have our thread pool. We're gonna mess with our new function here. So we're gonna do an assert macro and we're gonna have it panic, size greater than 0. So we're just leveraging the fact that assert will panic, right? So that's great. And then we're returning the thread pool. We've added some documentation. Okay, so they have some documentation too. And we're gonna just copy that. So what does it say here? Creates a new thread pool. The size of the number of threads in the pool, it panics. So panics if the new function will panic if the size is 0. We've added some documentation. Note that we followed good documentation practices by adding a section that calls out the situation in which our code panics. That's awesome. We talked about that in chapter 14. Try running cargo.open and clicking the thread pool struct to see what the generated docs look like. All right, let's do it. Cargo doc open. Nothing. I don't see anything. I think we have to maybe. It didn't open my browser, that's for sure. But I know we can do this. We could do reveal in Finder. And we could click it. Yeah, there you go. Thread pool. Check it out. Pretty cool, right? Panics. The function will panic if the size is 0. That's pretty awesome. Instead of adding the assert macros we've done here, we could make new return a result like we did with config new in the IO project, but we've decided in this case that we're trying to create a thread pool without any threads should be an unrecoverable error. We actually want it to be an error. If you're feeling ambitious, try to write a version of new with the following signature to compare both versions. This is if it was a result, right? Creating space to store the threads. Now that we have a way to know we have a valid number of threads to store in the pool, we can create those threads and store them in the thread pool struct before returning it. But how do we store a thread? Let's take another look at the thread spawn signature. All right, let's take a look. So our thread spawn signature, let's move this. I like the way they had it, just because it's a little clearer maybe. The spawn function returns a join. The spawn function. Sorry, they're looking at this spawn function here. The spawn function returns a join handle T, generic over the type T, where T is the type that the closure returns. Let's try using join handle 2 and see what happens. In our case, the closure we're passing to the thread pool will handle the connection and not return anything, so T will be of the unit type. The code in listing 2014 will compile but doesn't create any threads yet. we change the definition of thread pool to hold a vector of thread join handle instances. Initializing the vector with a capacity of size, set up a for loop that will run some code to create the threads and return the thread pool instance containing them. Whoa, hold on, let's take a step back. So the spawn function here, it returns a join handle where it's generic over type T. T is the type the closure returns, so it's whatever the closure returns. Okay, so here what we're going to do is we have our thread pool. We're going to store threads in it, right? Threads, and it's going to be a vector of type thread join handle, because we're saying the return type of this thread, right? It's going to be a unit type, and we're just stealing this from the implementation of spawn here, because that's what that returns. And since we're going to be calling spawn, we're going to have a similar return type, right? That's basically what that means. We need to pull in thread, use standard thread. For new, we've asserted the size, and then we're going to do let mute threads equal vector with capacity. We're going to use the size, so we're limiting it, right? That's the whole point of passing the size in. And then for, we don't care about the value, right? In 0.size, because we just have a count. We don't actually care about the number. We're going to go ahead and create some threads and store them in the vector. Create some threads and store them in the vector. We're just commenting that for now. And then we're going to return thread pool threads. All right. We've brought standard thread into scope in the library crate because we're using thread join handle as the result type of the items in the vector in thread pool. Once a valid size is received, our thread pool creates a new vector that can hold size items. We haven't used the with capacity function in this book yet, which performs the same task as vector new, but with an important difference. It pre-allocates space in the vector because we know we need to store size elements in the vector. Doing this allocation up front is slightly more efficient than using vector new, which resizes itself as elements are inserted. When you run cargo check again, you'll get a few more warnings, but it should succeed. All right, let's try it. So we did get a problem here because I used, there we go. Let's try it again, cargo check, and we're all good. A few warnings like they mentioned, but we're all good. A worker struct responsible for sending code from the thread pool to a thread. We left a comment in the for loop in the listing regarding the creation of threads. Here we'll look at how we actually create threads. The standard library provides thread spawn as a way to create threads, and thread spawn expects to get some code to send, some code the thread should run as soon as the thread is created. So thread spawn expects that code, that closure, right? However, in our case, we want to create threads and have them wait for the code that we'll send later. The standard library's documentation of threads doesn't include as any way to do that. We have to implement it manually. So again, in our case, we want to create the threads and have them wait for code that will send it later. We'll implement this behavior by introducing a new data structure between the thread pool and the threads that will manage this behavior. We'll call this data structure worker, which is a common term in pooling implementations. Think of people working in the kitchen at a restaurant. The workers wait until orders come in from the customers, and then they're responsible for taking these orders and filling them. Instead of storing a vector of join handle over the unit type instances in our thread pool, we'll store instances of worker struct. Each worker will store a single join handle instance. Then we'll implement a method on worker that will take a closure of code to run and send it to the already running thread for execution. We'll also give each worker an ID so we can distinguish between the different workers in the pool when logging or debugging. Let's make the following changes to what happens when we create a thread pool. We'll implement the code that sends the closure to the thread after we have the worker set up in this way. So we're going to define a worker struct that holds an ID and a join handle. We're going to change the thread pool to hold a vector of worker instances. We're going to define worker new function that takes an ID number and returns a worker instance that holds the ID and a thread spawned with an empty closure. In the thread new, In thread new, we'll use a for loop counter to generate an ID, create a new worker with that ID, and store the worker in the vector. If you're up for the challenge, try implementing these changes on your own before looking at the code. Oh, okay. I already kind of did. All right, let's try implementing it on our own first. So we need a worker struct. That holds an ID. Oh, it's a number. And a join handle. It's gonna be a single thread, right? Change thread pool to hold a vector of worker instances. Define a worker new function that takes an ID and returns a worker instance that holds the ID and a thread spawn with an empty closure. Okay. New takes an ID of type string, or sorry, of type U32, and it returns worker. And we're going to do worker ID thread is going to be thread spawn all right, and with an empty closure. In thread new, use the for loop counter to generate an ID. Okay, so we'll do ID. That's easy. Create a new worker with that ID and store the worker in the vector. So for that, we're going to do let worker equal worker new ID. And where do we have to store it? We have to store this in a vector. Okay, so we can create a vector out here. Call it let workers equal, or we'll call it let threads equal vec. And here we can do threads dot push worker. What does this say? Oh, usize. We could do that. Usize. What does it say? I think we can still use this, but we have to. What does it say? You can convert a usize to U32 and panic if it converts value it wouldn't fit. We can just make this a usize. And then what does this want? It feels weird. We'll probably have to change it. Constructs an empty vector with specified capacity. Oh, we already have threads. Duh. All right. Let's see if we did it right. Workers. We have to change it to workers. Workers. I guess we don't have to, but workers. So we've changed this to workers. We're going to change this to workers. 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 All right, so we got that part now. It's a thread worker. That's good. Our thread pool is going to do mutable workers, ID, workers push, worker new ID. Our worker takes, yep, we got that right. We got that right. And new takes a thread. It spawns this and it does that. So yeah, we did. I mean, we structured a little different, but perfect. We're good. We've changed the name of the field on thread pool from threads to workers because it's now holding worker instance instead of join handle instances. We use the counter in the for loop as an argument to worker new, and we store each new worker in the vector name workers. External code, like our server in the main file, doesn't need to know the implementation details regarding using a worker struct with thread pool. So we make the worker struct and its new function private. I did not do that. So that we'll want to do. So this can be private. Got it. Makes sense. All right. The worker new function uses the ID we give it and stores a join handle instance that is created by spawning a new thread using an empty closure. This code will compile and will store the number of worker instances we specified as an argument to thread pool new, but we're still not processing the closure that we get in the execute. Let's take a look at how to do that next. Let's make sure everything compiles. Let me move out of the way here. Good. All right, we're all good there. Pretty cool. This is looking pretty good. Okay. Sending requests to threads via channels. Now we'll tackle the problem that the closure given to thread spawn do absolutely nothing. They don't do anything. Currently, we get the closure we want to execute in the execute method, but we need to give thread spawn a closure to run when we create each worker during the creation of the thread pool. We want the worker structs that we just created to fetch code to run from a queue held in the thread pool and send that code to its thread to run. In chapter 16, you learned about channels, a simple way to communicate between two threads. That would be perfect for this use case. We'll use a channel to function as the queue of jobs, and execute will send a job from the thread pool to the worker instances, which will then send a job to its thread. Here's the plan. The thread pool will create a channel and hold on to the sending side of the channel. So remember, a channel has it works like a stream, right? It has a receiver and senders, many senders and one receiver. We talked about like a river, right? So the thread pool will create a channel and hold onto the sending side of the channel. Each worker will hold onto the receiving side of the channel. We'll create a new job struct that will hold the closures we want to send down the channel. The execute method will send the job it wants to execute down the sending side of the channel. In its thread, right? In its thread, the worker will loop over its receiving side of the channel and execute the closures of any job it receives. Let's start by creating a channel in the thread pool new and holding the sending side in the thread pool instance. We're going to see that below. The job struct doesn't hold anything for now, but will be the type of item we're sending down the channel. All right, so first we're going to go ahead and import use standard sync MPSC. So we have our worker, we have our thread pool. Our thread pool's got workers. We're going to have the sender, which is MPSC sender job. So we're going to need a new type job. We're just going to create a struct here, struct job. And we look, MPSC, multi-producer, single consumer. Again, multi-producers, and we have a single consumer, which is the receiver. So we have a sender here. We have a job. And then here in our new function, we're going to go ahead and instantiate that as a channel. So we're going to use a tuple. Let me move out of your way here. All right, so we have a tuple where we get sender, comma, receiver, and that's multi-producer, single consumer channel. We have our workers. For workers, we're going to push, right? We did worker new here. We can just simplify this. That's what they did here. We'll do the same thing. Simplify that, right? And then for thread pool, they're putting workers, but they're also putting sender. And you can see if when I don't have sender, it's going to complain. It's saying, hey, you're missing the sender field. So we'll just go ahead and use sender there. All right. Awesome. The thread pool new, we create our new channel and have the pool hold the sending end. This will successfully compile, still with warnings. All right, let's try passing a receiving end of the channel into each worker as a thread pool creates the channel. So we're going to pass the receiving end of the channel into each worker as the thread pool creates that channel. We'll know we want to use the receiving end if the thread that the worker spawned. Okay, so we know we want to use the receiving end in the thread that the worker spawned. So we'll reference the receiver parameter in the closure. The code won't compile yet. Okay, let's see what we're doing here. So we'll have to do worker new ID receiver. Okay, so it's not compiling yet, and that's because expected one argument. So we have to change worker, right? So worker, now it's new, needs to expect a receiver. What is receiver? It's a multi-producer, single consumer receiver of type job. Again, job's not defined, so it's not gonna, well, job's empty. So it is defined actually. And what is the worker gonna do? It's gonna go ahead and let thread equal thread. So we're just moving this thread spawn out, essentially. Thread spawn, we're gonna spawn it with empty closure. However, we're gonna declare receiver there. All right, we made some small and straightforward changes. We passed the receiving end of the channel into worker new. That's happening down here. We're passing the receiver to our new worker. Our worker is getting the receiver, right? And what are we doing? We're taking that receiver. Oh, I'm sorry. We're taking that receiver and we are putting it inside this closure that we're creating this this thread with. Let me change that to spawn. So the code is trying to pass. Oh, here it says let's if we were to run cargo check, we'll get this error. So cargo check, let sender receiver. Move occurs because receiver has type standard sync receiver job, which does not implement the copy trait. So the code is trying to pass receiver to multiple worker instances. That's happening here, right? It's trying to pass it, but receiver is a singular thing, right? This won't work, as you'll recall from chapter 16, the channel implementation that Rust provides a multiple producer, single consumer. This means it's got only one consumer. This means we can't just clone the consuming end of the channel to fix this code. Even if we could, that is not the technique we would want to use. Instead, we want to distribute jobs across threads by sharing the single receiver among all workers, right? Additionally, taking a job of the channel queue involves mutating the receiver. So the threads need a safe way to share and modify a receiver. Otherwise, we might get race conditions, which we talked about in chapter 16. Recall the thread safe smart pointers discussion in chapter 16. To share ownership across multiple threads and allow the threads to mutate the value, we need to use arc mutex over the generic T. The arc type will let multiple workers own the receiver, and mutex will ensure that only one worker gets a job from the receiver at a time. All right, let's check it out. So we have our thread pool, and so we have sender receiver channel, right? But we're gonna wrap that in. So we're gonna say receiver. We're gonna use shadowing, right, to redefine receiver. Receiver equals arc new, automatic reference counting, right? Mutex new receiver. So that allows us to access receiver in a safe way. That's why we have mutex there, and we're gonna have to pull it in, right? So we're gonna pull in multi-process channel, comma arc, comma mutex. They're all from the sync library, so we can use that shorthand. And then down here, we can just hover and it'll show us, right? Found struct. So what we want to do here is we're going to do arc clone, get the reference to that receiver, and let's see what we did here. So we have our receiver, arc new, our vector here, ID 0 to size. We're passing arc clone receiver. Let's see what this says. Mismatch types. Expected struct sync, standard sync, multi-producer, single consumer receiver job. Found struct, standard sync, arc, standard sync. So it's got that whole wrapper there. All right, let's see what we are doing here. It's probably because our worker is new, needs to be updated. And it does. So worker is new now. Instead of this receiver, it needs to take that type, right? And that type is arc mutex of this type job, right? In threadpool new, we put the receiving end of the channel in an arc and a mutex. For each new worker, we clone the arc to bump the reference count so the workers can share ownership of the receiving code. With these changes, the code compiles. We're getting there. Implementing the execute method. Let's finally implement the execute method on threadpool. First, let's make sure it compiles. We're all set. All right, let's implement the execute method. We also changed job from a struct to a type alias for a trait object that holds the type of closure that execute receives. As discussed in creating type synonyms and type aliases section of chapter 19, type aliases allow us to make long types shorter. Okay, let's try it. So we're going to change box to a type, or sorry, we're to change job. So job is going to be box, so there's misdirection, fn once, plus send, plus static. All right, what does that mean? Well, then it means we can simplify this here, right? Where f is of type job. So you can see here, threadpool, function execute. So we're gonna make a new function execute. F self, where f fm1 plus send plus static. And then we're gonna do let job equal box new f self dot sender dot send job dot unwrap. Okay, let's go over what we're doing here. After creating a new job instance, we're using the closure we get in execute. So execute gets a closure, that's F, right? So we're using the closure we get in execute. We send that job down the sending end of the channel. So we send that job. So we get that job. What is the job? It's that closure. We send that down the sending end of the channel. We're calling unwrap on send for the case of when it fails. So this might happen, for example, if we stop all threads from executing, meaning the receiving end has stopped receiving type messages. At the moment, we can't stop our threads from executing. Our threads continue executing as long as the pool exists. The reason we use unwrap is that we know the failure case won't happen, but the compiler doesn't know that. But we're not quite done yet. In the worker, our closure being passed to thread spawn still only references the receiving end of the channel. Instead, we need the closure to loop forever, asking the receiving end of the channel for a job and running the job when it gets done. Let's make the change shown in listing 2020 to worker new. So what are we going to do to worker new? We have our worker function. New takes the usize, the receiver, right? Thread. So here we're going to do thread spawn. So remember, we've seen this move, right? So thread spawn move, loop. We're going to loop here, and we're going to do let job equal receiver dot lock, because again it's mutex dot unwrap in case we can't get a lock, dot receive dot unwrap. So again, this could definitely panic. And then we're going to print ln worker got a job executing. ID job, and then we call it. All right, let's see what it says here. Oh, this also needs to be job equals, right? All right. Here we first call lock on the receiver. Right here. To acquire the mutex, and then we call unwrap to panic on any errors. Acquiring a lock might fail if the mutex is in a poisoned state, which can happen if some other thread panicked while holding the lock rather than releasing the lock. In this situation, calling unwrap to have this thread panic is the correct action to take. Feel free to change this unwrap to an expect with an error message that is meaningful to you. If we get the lock on the mutex, we call receive to receive a job from the channel. A final unwrap moves past any errors here as well, which might occur if the thread holding the sending side of the channel has shut down, similar to how the send method returns error if the receiving side shuts down. So the call to receive blocks, so there is no job yet. The current thread will wait until a job becomes available. The mutex over the generic T ensures that the only one worker thread at a time is trying to request a job. With the implementation of this trick, our thread pool is in a working state. Give it a cargo run and make some requests. All right, let's try it. Well, first let's change this. This actually has to be like this. So this actually has to be. All right, let's try it. Cargo run. All right, let's make some requests. Let's do this. Let's move this here. Oh, doesn't like that. All right, here, we'll just do this. There. Sleep. So hit sleep there. We'll hit Twitch here. This is still sleeping. We'll request sleep again. We'll go back. We'll go forward. We'll get a new one. We'll do 2 sleep ones. We'll go here. And we can see worker 1 got a job. And look, they're all executing. Pretty cool. That's awesome. Hell yeah. All right. Success. We now have a thread pool that executes connections asynchronously. There are never more than 4 threads created, so our system won't get overloaded if the server receives a lot. Oh, Sona, I missed it again. Guess I'll catch it on YouTube. Oh, no worries. We're still going. We're going late on this one. We're finishing chapter 20, but definitely catch it on YouTube. Thank you for stopping by. And thank you for the follow. All right. So we now have a thread pool that executes connections asynchronously. There are never more than 4 threads created. See, our system won't get overloaded if the server receives a lot of requests. If we make a request to sleep, the server will be able to serve the other requests by having another thread to run them. Note, if you open sleep in multiple browser windows simultaneously, they might load one at a time in 5-second intervals. Some web browsers execute multiple instances of the same request simultaneously for caching reasons. All right. After learning about the while let loop in chapter 18, you might be wondering why we didn't write the worker thread code as below. So if you look here, let's just take a look. The code we did write is using loop, right? So they're saying, why didn't we use the while let instead? This code compiles and runs, but doesn't result in the desired threading behavior. A slow request will still cause other requests to wait to be processed. The reason is somewhat subtle. The mutex struct has no public unlock method because the ownership of the lock is based on the lifetime of the mutex guard T within the lock result mutex guard T that the lock method returns. At compile time, the borrow checker can then enforce the rule that a resource guarded by a mutex cannot be accessed unless we hold the lock. But this implementation can also result in the lock being held longer than intended if we didn't think carefully about the lifetime of the mutex guard. So you can see here, what we're saying there is because the while let, right, lock unwrap, we want to actually just do it inside our loop, not as part of this there. The code in listing 2020 that uses let job receiver lock blah blah works because with let, any temporary values using the expression on the right hand side of the equal sign are immediately dropped when the let statement ends. However, while let holds it for that entire time, right? It does not drop temporary values until the end of the associated block. The lock remains held for the duration of the call to job, meaning other workers cannot receive jobs. All right, we are almost done. Ooh. All right, Let's go. The code enlisting. We're gonna power through. This is the final chapter. We're powering through. Graceful, shutdown, and cleanup. The code enlisting 2020 is responding to requests asynchronously through the use of a thread pool, as we intended. We get some warnings about the workers, ID, and thread fields that we're not using in a direct way that reminds us we're not cleaning up anything. When we use the less elegant Control-C method to halt the main thread, all other threads are stopped immediately as well, and even if they're in the middle of serving a request. Now, we'll implement the drop trait to call join on each of the threads in the pool so they can finish the request they're working on before closing. Then we'll implement a way to tell the threads they should stop accepting new requests and shut down. To see this code in action, we'll modify our server to accept only 2 requests before gracefully shutting down its thread pool. Implementing the drop trait on thread pool. Let's start with implementing drop on our thread pool. When the pool is dropped, our threads should all join to make sure they finish their work. The listing below shows a first attempt at drop implementation. This code won't quite work yet. All right, so let's implement that here. So we'll do implement drop for thread pool, and we need a capital D. Function drop takes the mutable self for worker in self.workers print ln shutting down worker ID. And then we're going to do worker.thread.join.unwrap. Okay. First, we loop through each of the thread pool workers. That's going to happen here, right? That's what this loop is. We use a mutable. For this because self is a mutable reference, and we also need to be able to mutate worker. For each worker, we print a message saying that this particular worker is shutting down, and then we call join on that worker's thread. If the call to join fails, we use unwrap to make Rust panic and go into ungraceful shutdown. Got it? Here's the error we get from the compile of this code. Let's just hover, it'll tell us. Move occurs because worker thread has type standard thread join handle, which does not implement the copy trait. Okay, the error tells us that we can't join because we only have a mutable borrow of each worker, and join takes ownership of its argument. To solve this issue, we need to move the thread out of the worker instance that owns thread so join can consume the thread. We did this in listing 1715. If worker holds an option thread join handle instead, we can call the take method on the option to move the value out of the sum variant and leave a none variant in its place. In other words, a worker that is running will have a sum variant in the thread, and when we want to clean up the worker, we'll replace the sum with a none so the worker doesn't have a thread to run. So we know we want to update the definition of worker like this. So we need to update worker. Thread is going to be an option that's either going to be a thread join handle what up Orame for the follow, appreciate it, thank you so much. Join handle, and we'll do this. This looks weird. Thread option, okay. Oh yeah, okay, that's right, because that's the type of thread. Join handle, right, got it. And we'll just go ahead and close that off. Thread, join handle, close that off. Why is it complaining? Option thread, join handle. What does it want here? Try adding a comma. No, I did that already. Struct worker. Oh, I'm doing it in the wrong spot. Duh. It's got to go up here. So this is gonna be an option now. And then down here, we're gonna need to make that an option. So you can see here, it's gonna complain. Let's suggest a second error, which points to the code at the end of worker new. We need to wrap the thread values in sum when we create a new worker. Make the following changes to fix it. So down here, thread, you can see we need to do sum thread. The first error is in our drop implementation. We mentioned earlier that we intended to call take on the option value to move thread out of the worker. The following changes will do so. So in our drop, we'll need to do, we have our println, then we're going to need to do if let, and we're going to try to grab some thread, right? Ahutsona in the chat said, what's next after the book? Great question. I have been thinking about it. We might do another project, maybe come up with a cool project that we want to try out in Rust. Maybe we'll do the exorcism.io exercises. Those are really fantastic, and try to use Rust for that. Maybe we'll build out, I don't know, maybe we'll try some crates. I'd love to try some existing crates, maybe to build something. Maybe we can try one of the Rust web frameworks. There's so much we can do. Maybe we can write some scripts that do some basic things. Maybe we can hit some APIs. A lot of options. And definitely, if you have any good ideas, put some in the chat. MD Trodev in the chat said, I've been going through 0 to production in Rust. Pretty good. Oh. Rust in Action is also super. I actually own Rust in Action as well. That's a great one. I'll probably read through that one at some point. I won't be able to do it on live stream because that one is a paid book. But if I can pull out some cool exercises and go through those, we could do that on stream. Some thread equals worker.thread.take. And then what we're going to do is we're going to do thread.join unwrap. There we go. Okay, so what we're doing here is we're trying to, if there is a thread available, we will take it, and then we will join and unwrap it. So as discussed in chapter 17, the take method on option takes some variant out and leaves a none behind in its place. We're using if let to destructure the sum and get the thread. Then we call join on the thread. If a worker's thread is already none, we know the worker has already had its thread cleaned up, so nothing happens in this case. Signaling to the threads to stop listening for jobs. So we need to actually tell them to stop listening, right? So with all the changes we've made, our code compiles without any warnings. But bad news is the code doesn't function the way we want it to yet. The key is the logic in the closures run by the threads of the worker instances. At the moment, we call join, but that won't shut down the threads because they loop forever looking for jobs. If we want to try to drop our thread pool with our current implementation of drop, the main thread will block forever, waiting for the first thread to finish. So let's talk about that. So we need a way to stop them, right? But right now, our threads loop forever. They're just constantly looping, waiting for jobs, right? The key is the logic in the closures run by the threads of the worker instances. At the moment, we call join, but that won't shut down the threads because they loop forever. That's what we're talking about. If we try to drop our thread pool with our current implementation of drop, the main thread will block forever, waiting for the first thread to finish, right? To fix this problem, we'll modify the threads so they listen for either a job to run or a signal that they should stop and exit the infinite loop instead of job instances, or channel will send one of these two enum variants. So right now, it's expecting a job. If it doesn't see a job, it just sits there and waits. But we're going to actually change it. So instead of just taking jobs, it can take a message to either run a job or terminate. The message enum will be either a new job variant that holds the job the thread should run, or it will be a terminate variant that will cause the thread to exit its loop and stop. We'll need to adjust the channel to use values of type message rather than job. All right, that's easy enough. Let's create this enum. So let's see, we're dealing with jobs here. Let's do it up here. Let's do it right at the top. Enum message. It's going to be new job, terminate. All right. And again, this is just an enum, so we can make these strings whatever we want. The message enum will be either new job or terminate. We'll need to adjust the channel. So, okay, so now where are we handling jobs? Wherever we have jobs, we're going to use a message. So instead of a job here, we're going to do a message. So in our execute for our thread pool, so first things first, our execute is going to create a, let's see, execute takes a function, send static job equal box new F. Okay, that's right. Sender, send, and then instead of sending the job, we're gonna wrap that in the enum message new job. Sender here is gonna be let's see. Our thread pool will need to change, right? Yeah, so thread pool workers, and then sender will be a sender of type message. We got that. That's good. All right, so this is right. We'll take a look at this in a second. Let's update worker. So for worker, new is going to receive, instead of job, it's going to receive message. Here, this is all good. This is the same. Instead of this here, where we're doing, let's see, message. Okay, they changed this quite a bit. So you have respawn where you're looping, and then we're pulling out the message instead of the job. And then we're doing a match on the message. So let's do that here, because we need to know if we're going to terminate. So for that, we will do match on the message. And the first thing is we get message, new job, right? And then we'll have the job, and then we'll just do what we were doing before, which is, well, there we're adding a print here. Worker got a job. Or am I? Gotta go, but so good to find someone who streams Rust. Oh yeah, thank you for stopping by. I really appreciate it. And thank you for the follow. So job here, executing, and we're just gonna give it the ID. And then here, we're gonna do job. So we're gonna execute that job. Otherwise, what's the other option? We get message terminate, in which case we wanna stop. And so we're gonna just print out here, worker blank, was told to terminate. And then we'll break. And then we have that thread there. So the other thing that was messed up was down here, which is all fixed now. All right. To incorporate the message, we need to change job to message in two places: the definition of thread pool and the signature of worker new. The execute method of thread pool needs to send jobs wrapped in the message new job variant. Then in worker new, where message is received from the channel, the job will be processed if the new job variant is received, and the thread will break out of the loop if the terminate variant is received. With these changes, the code will compile and continue to function in the same way as it did after listing 2020, but we'll get a warning because we aren't creating any messages of the terminate variety. We haven't done that yet. Let's fix this warning by changing our drop implementation to look like below. So here we have drop, we have our worker. We're going to change this a bit. So first we're going to print out println sending terminate message to all workers. In self.work. Oh, we'll need that still. Okay, so let's do this. So we do for we don't care in self.workers, self.sender.send message terminate. Unwrap. All right, so for all the workers, right, self.send. So we send that many messages. We send that many messages to terminate. So for every worker, we want to send a message to make sure we stop all of them. We're not targeting a specific worker with that message. We're just queuing up in the queue. We're queuing a bunch of terminate messages. That's all that is. Then we're going to log println shutting down all the workers. And then for worker in mute self worker, println shutting down worker, worker ID, if let some thread, worker thread take. So it does it finishes the last job, and then we're good. We're now iterating over the workers twice, once to send one terminate message for each worker and once to call join on each worker's thread. If we tried to send a message and join immediately in the same loop, we couldn't guarantee that the worker in the current iteration would be the one to get the message from the channel. To better understand why we need two separate loops, imagine a scenario with two workers. If we used a single loop to iterate through each worker, on the first iteration, a terminate message will be sent down the channel and join called on the first worker's thread. If that first worker was busy processing a request at the moment, the second worker would pick up the terminate message from the channel and shut down. We would be left waiting for the first worker to shut down, but it never would because the second thread picked up the terminate message, deadlock. Basically, since we're just throwing 4 messages to close onto the thread, we're just putting 4 there. We don't know who's going to take that. It's not like they're assigned to a thread. So what's going to happen is as a thread frees up, it's going to take a terminate. And you need each of the threads to free up and take a terminate. So you need 2 loops because you need to just say, hey, shoot all 4 onto the queue, then run through each thread and one at a time have them pull a job off. If you didn't do that, again, you could run into an instance where a thread pulls a terminate or pulls 2 terminates right before something else pulls it. Obviously, you can't pull 2 terminates, but that's the concept there. To prevent this scenario, we first pull all of our terminate messages on the channel in one loop, and then we join on all the threads in another loop. Each worker will stop receiving requests on the channel once it gets a terminate message. So when we can be sure that if we send the same number of terminate messages as there are workers, each worker will receive a message before join is called on its thread. To see this in code in action, let's modify main to accept only 2 requests before gracefully shutting down the server. All right, let's do it. So in main, we have our listener, we have our pool of 4 stream listener, stream, pool, execute, handle, connection, stream. We're going to do take 2. Listener incoming dot take 2, and then we'll call print ln shutting down. So yeah, we obviously wouldn't want to do this in the real world, but let's try it out. So cargo run, we're running there. 1 request, 2 requests. Oh, well, actually, it already got 2. Right, and then it shut down. There you go. So I got the 2 requests and it shut down. Pretty cool. The take method is defined to the iterator trait and limits the iterator to the first 2 items at most, right? The thread pool will go out of scope at the end of the main and drop implementation will run. Start the server at cargo run and make 3 requests. The 3rd request should error and your terminal should see the output. You might see a different ordering of workers and messages printed. You can see how this code works from the messages. Workers 0 and 3 got the first 2 requests, and then on the 3rd request, the server stopped accepting connections. When the thread pool goes out of scope at the end of main, its drop implementation kicks in, and the pool tells all workers to terminate. The workers each print a message when they see the terminate message, right? So they print a message when they see it, and then the thread pool calls join to shut down each worker thread. Notice one interesting aspect of this particular execution. The thread pool sent the terminate messages down the channel. Let me go back here. Let me move this so we can take a look. I want to just get out of your way here. The thread pool sent the terminate messages down the channel. And before any worker received the message, we tried to join worker 0. Worker 0 had not yet received the terminate message, so the main thread blocked waiting for 0 to finish. In the meantime, each of the workers received the terminate message. When worker 0 finished, the main thread waited for the rest of the workers to finish. At that point, they had all received the terminate message and were able to shut down. You can see that here. So let's look at it line by line to what they're saying. Worker 0 got a job. Worker 3 got a job. Shutting down. Sending terminate message to all workers. Shutting down all workers. Shutting down worker 0. Worker 1 was told, 2 was told, 0 was told, and 3 was told. Shutting down 1, 2, and 3. So thread pool sent the terminate message down the channel. And before any worker received the message, we tried to join worker 0. Right? Worker 0 had not yet received the terminate message, so the main thread blocked waiting for worker 0 to finish. 0 got a job. had to finish. In the meantime, each of the workers received the termination. So they all get their termination, right? When worker 0 finally finished, the main thread waited for the rest of the workers to finish. At that point, they all received the terminate message and were able to shut down. Congratulations, we've now completed our project. We have a basic web server that uses a thread pool to respond asynchronously. We're able to perform a graceful shutdown of the server, which cleans up all threads in the pool. Here's the full code for reference. And we got that. We got it. We did it. We did it. Fam, we did it. We could do more here. If we want to continue enhancing the the project, here are some ideas. Ooh, potential future streams. Add more documentation in thread pool. Boring. Pretty cool. Add tests to the library's functionality. Change calls to unwrap to more robust error handling. That could be cool. Use thread pool to perform some tasks other than serving web requests. Find a thread pool crate on crates.io and implement a similar web server using the crate instead. That could be awesome. Then compare its API and robustness to the thread pool we implemented. I'd be down for that. Wow, we did it. Let's read this summary. This is our last summary. Ooh. I think we have to read it in a cool voice. I don't know. That's just how I'm feeling. You might hate that, but I think it's going to happen.
Well done. You've made it to the end of the book. We want to thank you for joining us on this tour of Rust. You're now ready to implement your own Rust projects and help with other people's projects. Keep in mind that there is a welcoming community of other Rustaceans who would love to help you with any challenges you encounter on your Rust journey.
Wow. We are Rustaceans.
Welcome, Rustaceans.
Woo, we did it. The last summary. Wow. Appendix. We're not going to go there. We did it. We finished the book. Woo. If you've been following along, yes. If you still have to catch up, you're fine. It's all available for you. But this is great. We finished the book. Now we are open. We've learned a bunch of stuff. A lot of it went by very fast. I'm going to have to review it. I'm going to keep this code. I'm going to push it up onto GitHub. That's where you can find it. But we did it. We made it all the way through the book. Check this out. Look at this. All these chapters. We didn't know. We didn't know when we started if we were going to do it. We did it. We made it all the way through the book. We had chapter 10. That was a crazy chapter, right? We had our other crazy chapter, chapter 19. That was a crazy chapter. We did it. We made it all the way through. Thank you for following along. Thank you for joining me in this. Of course, the reason I did this, I didn't want to do it alone. I was going to do it anyway, so I was like, I might as well just stream it. So really, thank you for joining. And again, we did it in the beginning, but we got to give another shout out. Steve Klobnik, Carol Nichols, and anyone from the Rust community that contributed to this book. It's been awesome. We were able to make this really cool web server, right? We've learned a lot. We did the Rustlings exercises. We've done so much. We finally finished the book. It feels great. People have been asking, what are we going to do next? We'll try some exercises. Maybe we'll try that stuff at the end of chapter 20. We'll try to build something. Put some suggestions in the comments if you have any ideas for what to build. We got some pretty ambitious ones. I don't know if we're going to be able to build a Bitcoin or cryptocurrency dashboard, but that's a cool idea. We could build it over the course of a long time with maybe a few different technologies. But yeah, put some ideas for what we can build. Advent of code. Yes, we could do Advent of code. That would be a great one. Go through Advent of code for Rust. I know there's someone on Twitch doing that. But yeah, I think that'd be really cool. Also, exorcism.io. This is another one I was thinking about. I don't know if you have seen this, chat, but there is this thing called exorcism.io where you can go through different exercises in the language of your choice. And so you pull down different ones, and it's done with test-driven development. So this could be a really fun one. It'll kind of be like Rustlings. It'll actually be a lot like Rustlings, but it could be pretty cool. Or we could just try building something. Maybe make some requests to an API. Maybe we can parse some files. Maybe we can do something fun, like write some cool scripts to automate some of the boring stuff. But thank you so much for following me in my journey to do the Rust book. It feels great having finished it. I'm excited to use Rust. I'm excited to see if I can use it in production at my company or whatever for some projects. So definitely excited for that. Again, if you've missed any of the episodes, they're all here. They're all on YouTube. They're long because they're just the streams, right? I just cut out the basic intro and just toss it up. So luckily it's not too much work on my end, but what that means is for you, it's a little maybe more difficult to parse through because they're long, but watch them on 2x speed, watch them on 1.5 speed, skip around, do whatever you want. They're all here. They're all labeled. This one will be going up tomorrow. So you'll see that there. We'll call it, finale, and we'll wrap that up there. More to come. I'm planning on being here next week, so we'll just keep going. We'll figure out something to do. If anything, we'll review the code. We'll hack on some of that stuff, but don't worry. We're going to keep this thing going. We may even try some other stuff. Maybe we'll try some other languages as well. So you all know I've been working with Elixir a lot, so maybe we'll do a little brief intro to that as well. Who knows? But I'm excited to do more Rust. I feel like completing the book has been a great achievement. If you've been following along, congratulations, pat yourselves on the back. This was definitely an undertaking. We started in September. It's now, I don't even know what month it is. I'm out of it. No, it's now March, right? Mid-March. So we've come a long way. So again, all the videos are here. Follow on Twitter. You'll get posts for when I go live. If you like what you see on YouTube, like and subscribe at Classic Streamer. Like and subscribe, but you got to say it, right? You got to say it. Everyone's got to say it. But yeah, we've been having great comments. So leave some comments there. Again, we're live 9 p.m. to 11 p.m. if you want to catch us on Twitch. So here is the Twitter. Here's the GitHub. I'll push this code up as well. And that's pretty much it. We did it. Final chapter, chapter 20. Again, pat yourselves on the back. If you've been here for the whole ride, I want to see a comment down below. I want to see you say, yo, we did it. We did the book, whatever. If you've been following along, I really appreciate it. It's been amazing to see people follow along because like I said, they're long videos. More content to come. We'll keep it going. It's been really fun. We're not stopping here. This is just the beginning, right? We just did the book. This is just the beginning. We're going to continue. So thank you for joining me in my Rust journey of learning Rust. I've been really enjoying it, and now I'm excited to use it. That's all for tonight. We did it. Woo! We finished the book. Let's go. It feels so good. I don't even know if I'm ready to end, but I am. We did it. Final chapter. Thank you again for hanging out, learning Rust with me. More to come, onward and upward. Just the beginning. Let's keep going. Keep it real, and have a good night.